Welcome back to the second session, the afternoon session of the Schawlow-Townes Symposium. My name is Paul Corkum. I'm also from the University of Ottawa, and I will officiate at the second part. So our first speaker this afternoon is Reinhard Dörner. Reinhard Dörner studied physics and philosophy. I don't know if it's really philosophy or if it's just called physics and philosophy together. Did you really study philosophy? Okay. Physics and philosophy at Frankfurt and Aachen. In I guess the early 90s. He received his PhD in 1991, so I guess it was in the late 80s, from the University of Frankfurt. In 1995 to 98, he went to Berkeley at the Lawrence Berkeley Laboratory, where he had a Feodor Lynen, I should know how to say this, scholarship from the Humboldt Foundation. In 2002, he became a professor at the Institute of Nuclear Physics at the University of Frankfurt, where he still is. His research interests are in atomic, molecular physics, and many particle dynamics. And in particular, he's known for kinematically complete experiments using a technique called COLTRIMS, and I'm sure he will introduce it to us, so I won't describe the initials to you. He'll tell you, I'm sure, what the COLTRIMS is. I first knew Reinhard, I believe, directly in probably, didn't look it up, but probably about 2000. And in the year 2000, he telephoned me from Frankfurt. I had never met the person, I don't believe. And he'd been doing some experiments, kinematically complete experiments using strong fields and seeing recollision. And I was very excited about it, of course. We discussed it quite a bit, and maybe by the time we hung up that time, I don't remember exactly, we had decided that we would try a joint experiment. So Reinhard, I couldn't believe how this worked. These people from particle physics and nuclear physics, they just build big detectors and ship them all around the world. And so he said, I'll build a detector and we'll ship it to Ottawa. And I just thought this was impossible. But it turns out you build a detector and ship it to Ottawa, and we have a COLTRIMS detector in the bottom of our laboratory at NRC as a result of this. So I began to learn what these particle physicists and X-ray physicists and nuclear physicists really knew. So it was very good, and of course it's had tremendous influence on my research, so I'm happy to have him here, on the staff and personnel that come to the lab. We have visitors still coming back and forth from Frankfurt, and of course Andre Stade, sitting right behind you, is a result of that telephone call that was from about 2000. Anyway, it's great pleasure to welcome Reinhard and have him speak.
Yeah, thank you, Paul, for this very nice introduction. I still remember first having met you in person in Monterey on the meeting. There we started to talk, and I still have very fond memories of that. So when I received the invitation to speak here half a year ago or so from Bob and from you, I didn't know about your symposium, and I have to say after this morning and seeing the symposium, I'm really impressed, and I'm deeply honored to be chosen as a speaker here. So thank you for the invitation. So here's what I'm going to talk about. It's not directly photonics, but it's using photons. It's using photons to image molecules by detecting basically the aftermath after a photon or many photons have interacted and destroyed molecules in many pieces. And I will show you how we can learn from all the fragments from a molecule which you blow up about its structure, and how light preserves the bound state of a molecule and takes it to a detector so you can see the wave function and parts of the wave function of that molecule. So the molecules I will talk about are kind of small from a chemist perspective, so I will talk about diatomics and some chiral molecules. And if you look at the wave function of a molecule, well, that's the wave function, and the capital R's are the positions where the nuclei are. And then there are the small r's, and that are the positions where the electrons are. So if you want an image in the chemistry textbook, you usually find that. But of course, what you really would want to know is not only where the nuclei are, that's the structure. I mean, ideally, you would want to have in such a picture also the positions, if that makes sense, the positions of all the electrons. Of course, we are far from that goal. But with a picture, I mean really everything, all the coordinates. We are far from that goal, but that's kind of the final thing. So what I will show you today is first how we get knowledge about the position of the nuclei. So that's the structure of the molecule. And with a technique called Coulomb explosion imaging, and I will guide you through that. And then I will use that to show you a molecular movie to see how the nuclei move. I picked one example. And then I will move to the electrons, which you cannot see here besides that kind of blurry thing around here. And I will show you how we can image the position or the momenta in one instance of two of the electrons in a simple molecule in H2. And finally, since this is Ottawa, I have to talk about very short timescales, and that's new and kind of loosely connected to the rest. Okay, so let's go. We want to know the electrons and the nuclei and how they are correlated. So to do that, you have to measure this, and that is where coincidences come in. That's what I call coincidence imaging. So at the end, you have to measure the nuclei and the electrons and do that for each individual molecule in coincidence. So the technique we use is the following. We come in with light, and we use very different types of light. I've outlined it here. So sometimes we use single photons. That's from synchrotron radiation. Single photon absorption, that are photons in the energy range up to a few kilo electron volts. We also use femtosecond Tie-Sapphire lasers, so 1.5 electron volts. So there you need many photons to destroy a molecule. And we also use free electron lasers, so that are many photons, but of high energy X-rays. That's done at the free electron laser in Hamburg, the X-FEL. So we shine our light, whatever it is, onto our molecule that kicks out electrons. And in response, now there is a lot of positive charge, and the thing will blow up. So you get many positive and negatively charged particles flying around, and we want to capture those and then conclude back on what the initial state was. And possibly also learn about light-matter interaction from these fragments. So here's how you do that. It works all in the gas phase. Whoops. I had to get another computer, so I don't know how to click here, so here it comes. So that's in the gas phase, very good vacuum, 10 to the minus 10 vacuum. You put a supersonic gas jet in, which means you have individual molecules flying through your chambers, and you shoot in your laser pulse or your synchrotron or your FEL here, and you have an interaction point here where everything happens. You blow out the electrons. The blue one is one example of an electron, and these are the positively charged fragments. And you have a weak electric field, some 10 volts per centimeter or so here. The whole thing is about this size. And the field projects the positively charged particles onto one detector, and the negatively charged, well, the electrons, to the other detector. And then what you measure for each of these particles, you measure the time of flight it takes from the hit of the laser pulse to the detector and the position of impact, and you do that in correlation between all of them. So for each molecule which you destroy, you have an array in which you have all the positions here of all the particles and the time of flights, and two positions, one time of flight. From that you can, if you know the fields, you can recalculate its initial direction and energy or momentum. And that's what you do, and then you have a huge data set, event for event, molecule for molecule, where you have all the information. Well, that's inspired from high energy physics. If you search for new particles at CERN, that's what you do. You have a big detector, shoot in, make one collision, and get all the fragments, and that's the equivalent of that for molecular physics. That's we have called it a kind of a cloud chamber, which catches everything. Okay, let's use it. Let's first use it to look at that detector, to look at the ions. And from the ions, you get the structure by a technique called Coulomb explosion imaging. And the idea is very simple. If you rip off the electrons kind of instantaneously, then the particles repel each other. And the forces which drive this explosion are simple. If it's highly charged, it's just 1 over the distance is the repulsion. You have the forces, and then you can calculate these trajectories back. If it's still some electrons binding, then it's more complicated. And I will show you that that works to determine structure for small molecules and some bigger molecules. So these are the examples which I've selected. And well, there are some fun examples which you cannot get the structure otherwise. Okay, a little more detail about how that works. Well, that's the quantity we are after, the square of the wave function as function of, if it's a diatomic molecule, as function of internuclear distance. And we don't want the equilibrium internuclear distance, which you would get from spectroscopy, but we want the distribution of internuclear distances. So really the wave function, which for ground state would be, for example, this Gaussian-shaped distribution. And it's actually quite easy to get it. And the idea is not new and not from us. It's very simple. If you take off the electrons, then you have 2 singly charges sitting here at a distance capital R. And the potential energy in there is 1 over that distance times some constants. And that potential energy is converted to kinetic energy as it flies apart. And the kinetic energy you can measure on our detectors. The 1 over the distance at the instant when you instantaneously remove the electron is just 1 over the kinetic energy which you measure. That's it. And that is much more precise than the average value. That's not the average value. That's the internuclear distance for each individual molecule which you destroyed. And a little more detail, if that is the internuclear distance, that's the interaction potential, for example, of H2. So the bound state would be kind of a Gaussian sitting here with that distribution. Now, you rip off the 2 electrons, which means you go to that potential energy curve, which is just 2 protons. That's just 1 over distance, that's this. So you go up here, the particles roll down here, and you project position to energy, which you measure. Something you want to know to basically a position on your detector, or width of position. So that's the idea. Yeah, you might wonder if that's a classical picture, if maybe Heisenberg has something against that scheme. And I can assure you there are some tricks, but in principle, there is a quantum version of that. I will not guide you through it, which is in accordance, of course, with the uncertainty relationship. So does it work, and how good does it work? So here is, from the chemistry textbook, the most simple molecule in the universe, H2 plus just 1 electron, which you can kick off. That's a potential energy curve, and that is, from a chemistry textbook, the ground state, and then the excited vibrational states of the H2 plus. Internuclear distance is plotted here. So 1 nucleus sits here, and that is, if you read it this way, is the density distribution. It's the square of the wave function, density distribution of the second nucleus. Now, well, of course, all of that is known, and that's the vibrational spacing, which you get, these numbers you get from spectroscopy. Of course, all of that is known, but we are proud experimentalists, and so we want a picture of that. So Lothar Schmidt some years ago set up to actually image that. And now I will show you as the data points he got. That is what you actually get out of that technique. It's a density distribution. You can measure the energy by some trick, which is too lengthy to explain now. And then you see the density. And you see that's the ground state of H2 plus, and the excited state is indeed, there are 2 maxima and a node in between and everything. You see all the details of all the vibrational wave function in there. So it works. Well, there's one number you have to remember. Size of a molecule, 1 angstrom, because now I show you, well, that's all known. Now I show you a molecule which is not all known, but still a diatomic, but a very interesting one. So remember 1 angstrom as size. Now we go to a molecule which, well, depending on your background, you might think doesn't exist. The helium dimer. There are 2 helium atoms being bound. There is no covalent bond. It's bound by the van der Waals interaction between these 2 helium atoms. So one polarizes the other one, and you have very, very weak van der Waals interaction. You can calculate the van der Waals interaction. It's indeed attractive. It has a potential minimum at 3 angstrom. Remember, hydrogen was here. But this scale is very, very different from any real molecule. I mean, a real molecule would be bound by, let's say, 2, 3 electron volts, and this is bound by 1 milli-electron volt. Well, this was wrong. It's not bound by 1 milli-electron. The bottom of that potential calculated is 1 milli-electron volt. Though the molecule actually, if it exists, doesn't sit down here, but in addition to this bottom here, of course, you have zero-point motion in quantum mechanics. You cannot put a particle at rest. So if you calculate the zero-point motion, it has to live in there. Well, that's for this calculated, that theory, calculated potential, that's a zero-point motion. Well, look at the numbers. It's almost the same. What does that mean? That means the binding energy is just the difference between these numbers. That is where this state actually is here. And so it was for a long time under dispute which of these numbers is bigger, whether this thing has a bound state, meaning a state below here, or above here. But that is settled for 30 years. It does exist, and people have seen it actually. And now we are after what's the wave function. That's the binding energy. It's nano-electron volts. Well, the calculated binding energy, exact values under dispute. I will show you some results. Now, what are the wave function of that? If it were a normal molecule, you would have some Gaussian in here. But if the binding energy is here, the wave function looks completely different. And to see it, we really have to change scale. So watch that. We zoom out to see the wave function. So in here, that's the potential, and that is a calculated wave function out here. And out there, where the particles live, the potential is 0. I mean, it's too far away. Well, that's theory. So it's better to think of that as 2 helium atoms sitting at large internuclear distance, being super weakly bound nano-electron volts. And if you come from chemistry, here are some other units you might like more for predictions for the binding energy. So that's what we are after, because that is such a peculiar quantum system, completely delocalized thing, which, of course, nobody has seen before. And here's a comparison. That's not cheating. That's to scale. You could slide through a stretched DNA through that thing. So let's make it and keep an image. And here's from Coulomb explosion imaging the wave function. And the 2 lines are 2 calculations. There are many calculations around which differ. And you see these 2, even though they are much used, are not exactly spot on. But the wave function indeed extends to basically infinity. To understand, and from that, you can get the binding energy, as I will show you now. And you get an experimental value, which is, if you look at this, well, I will show you in a second. So these are the 2 PhD students who did that. There are 2 experiments basically in here. One done with a free electron laser Coulomb explosion imaging, and one with a femtosecond laser for technical reasons to get the accuracy. So let's look at that potential again. So up here is the same thing as this line here, the potential. And this binding energy of nano-electron volts is here. So it's basically on the baseline. So to see where it really is, we have to zoom out and to zoom out. And now I've changed the scale from milli-electron volts to micro-electron volts. So 100 nano-electron volts is here. So that would be the binding energy. That is the potential which goes down here and here. So this calculated state would have that energy. And this is the wave function on there. Now, if it were a classical particle, what it would do is it would bounce back between the inner and the outer turning point. You would roll here, and it would live in that classically allowed pocket. Now, this is quantum mechanics. All these particles out here, they tunnel in here. What does it mean? If you have a particle here, it means it has a total energy, which is this red line. It has a potential energy, which is 0. And so the total energy, the red line, is the sum of potential energy and kinetic energy. So it means it has a negative kinetic energy. Well, it doesn't make sense. A negative kinetic energy, that's tunneling. That's quantum mechanics. So all these particles out here are tunneling in a classical forbidden region. And from a physics perspective, I really like that, because that shows, every count here shows you have caught a molecule at a position where it shouldn't be classically. So like the electrons I'm made of have some probability to be on your seat. We all know that, of course, from our quantum course, but we consider it to be negligible. And for this thing, yeah, they are really out there, out in the tunnel. You can catch them and find them there, actually. Now, what you also know from probably everybody who has a physics education has calculated what the wave function out here is. It's just an exponentially decaying wave function, and that is, if you don't remember it, is the tunneling wave function of any wave function. If you have no, I mean, hydrogen would look the same asymptotically, where the potential is gone, it just exponentially drops, and what is in there is the mass and this energy here. So we switch to a logarithmic scale, so we see that exponential here, it's beautiful linear on a logarithmic scale, and from the slope you get this number because the mass is known. You can fit, and you get a number from it, and you can compare it with these two calculations I've shown you before, and you see they were kind of off, meaning they had the kind of the wrong binding energy, slightly wrong. And you get the number, and here are the numbers for this binding energy. These are over the years. The calculated numbers for this binding energy, so up here would be not bound. They all agree it's bound. But it changed over the years, and recently, last 15 years or so, people kind of agreed that the binding energy should be here, and our experimental point agrees with the best calculations, and that's the number. Now, I'm not a spectroscopist. I'm not so excited about the exact number, but what is fun is to think for a moment what you have to put in a quantum chemistry calculation to get these extremely small numbers right. And here's a list what's in that calculation. First, you cannot use the Born-Oppenheimer approximation. Okay, that's not so surprising. You have to account for the fact that the electrons move the nuclei around. Okay, that you can do. Then you have to calculate relativistically. That's surprising for helium because it's usually not considered to have any relativistic effects. You have a factor of electrons are a factor of 100 below the speed of light, but okay, you can do that. And this part here is fun. You have to take part of retardation. What is that? That's the fact that the information or the Coulomb potential at one acting on the other takes some time to travel over there. This thing is so big that the retardation, that the interaction is not instantaneous, but it takes some time, and you have to put it into the calculation, and these people did. And then you also have to take care of the coupling to the vacuum field, that's QED. And if you do all that, then you end up with these points, which are in agreement with the experiment. And sure enough, we should get better accuracy to finally nail down one of these calculations. Okay, if you have the square of the wave function, you can do amazing things with it. Let's look at the Schrodinger equation. I mean, this is a Schrodinger equation as you know it. And usually the way you read the Schrodinger equation is you have the wave function and you have the potential. So you take the potential, put it in, and then you calculate the wave function and the energy. But of course, it's just math. You can do it the other way around, because in the experiment, now we have the wave function. We know it's a ground state, so it's real valued, so we can take the square of it, square root of it, then we have the wave function. So we have the wave function. And if you have the wave function, you can take the second derivative, so it's just the difference between the points, okay? So we also have that, and we have the binding energy. So we have everything which is in the Schrodinger equation. So we can reorder it and get the potential. Kind of strange way to use the Schrodinger equation, but why not? So let's do it. That is a straight line through our data. That's a calculated interaction potential, van der Waals potential, and these are the data points which you get from our wave function. So you can actually map potentials. It works for helium. You go, same trick. You go to neon. That's a factor of 5 more tightly bound to neon atoms. Van der Waals is much stronger. Spot on, you get the potential. And you scale up by another factor of 1,000. So you go to hydrogen, measure the wave function, and that's the hydrogen interaction potential. So if you have the wave function, it's nice. You can get the potential if you want. That's 2 particles. Let's look at 3 particles. 3 particles for helium is a very exciting thing, and it was first predicted by Vitaly Efimov, a person from at St. Petersburg at that time, a nuclear physicist. And he's calculated that if you have short-range interactions between particles, he was thinking about nuclei, but it can as well be anything which has a short-range interaction like van der Waals. He predicted that if the potential the binding energy goes to 0, which for helium it almost does, as you have seen, then a strange type of states, which today are called Efimov state, arises, and there is an infinite tower of states where the 3 particles are at huge distances, all 3 at the same time, and that should exist in principle in nuclear physics. And soon after that, people calculated helium and said, well, helium is probably the only system in the universe where this strange quantum effect, which Efimov calculated, is realized in a real system. And then after that, some 10 years ago, the cold atom people got very excited about it because they can tune the interaction strength, kind of modify the van der Waals if you want. And they created artificially in cold atom traps, they created these Efimov states, couldn't image it, but could measure the binding energy, and a whole industry grow where you could confirm this quantum effect. Now, we went out to confirm that helium actually is of that type, of that Efimov type, or has a state. So we imaged that. We first made it, long story, but I just show you the final picture. So that are 3 helium atoms, and you have to watch the scale. This is angstrom, 100 angstrom. Well, there is a state of helium-3 where the 3 helium atoms are at tremendously big distances. This is theory, that's the experiment. The inner part here, our detector is blind, so that's not disagreement with theory. So the range of the interaction forces is in here. So 3 helium atoms can be at huge distances. And you might ask, why don't they fly apart? There is no force out there. It's flat. But they don't because there is a tiny, tiny contribution of the wave function in here. And this tiny contribution of the wave function holds everything which is out there, which only works in quantum mechanics. So they're all tunneling simultaneously, if you want. OK, if you would put the hydrogen in there, you couldn't see it. It would just be a spot. It's really angstrom. So it's a huge beast. OK, let's go to even bigger systems to image them. And they're an interesting species are chiral molecules. So this is a chiral molecule made of a carbon in the center, and then hydrogen, bromine, fluorine, and chlorine. And if you do that, you can make it either a left-handed or right-handed geometry. If you cook it in wet chemistry, of course, you get a racemate, which is a 50-50 mixture of these 2 enantiomers, because they are energetically degenerate, if it were not for the weak force. OK, so we had our colleagues in the chemistry department cook it, and we put it into the COLTRIMS machine, shot a femtosecond laser, 2 times 10 to the 15 watts per square centimeter, ripped off many electrons, 5 in this case, and looked on the detector. And the goal was to see from that racemic mixture if we could really see the chirality for each individual molecule, which is otherwise almost impossible, or is impossible to do on a single molecule basis. And that's Martin Pitzer, whose PhD thesis this was. So here's what you get. That's kind of the sticks and balls and sticks model. And these are the data. And the data now are not in position space. It's a little misleading. What I've plotted, each dot here is 1 click on the detector. And what is plotted is the momentum, so the direction and the length of the momentum vector. And what that shows you that the particles are really flying along the bonds, as you would expect, because they're repelled by Coulomb force. And you nicely image, if you look just in momentum space, you image the structure of that 3D molecule. And you can see it's good enough that you can distinguish the 2 enantiomers. So you can sort in your data set from the racemate. You can sort for each individual molecule. Was it right-handed? Was it left-handed? And so on, even though they have the same energy. Well, that's kind of nice. can we scale that up? So here's the biggest molecule we have done so far. It's called 2, because the nitrogen is here, iodo-purine. So it's carbons here, 1 nitrogen, and iodine here. And you have protons sitting out here. Now we want to charge that up and explode it. And to do that, we went to the free electron laser XFEL in Hamburg. And from the M shell of, that's like 1200 eV photons, many from that machine, all within 20 femtoseconds, you have 10 to the 14 watts per square centimeter, and that spits out many electrons. So you create here, where you have a high set target, you create a very high charge, and then in response to that high charge, the charges from here will flow over, and you eventually charge up that thing. And as first response, the protons will go. And then as you further charge it up, the whole ring will explode. And now let's look on the detector, what you get. The coordinate system is fixed such that the iodine determines this axis. The nitrogen determines the upper half sphere. They span the plane. And now in that plane, you plot the momenta. It's not position. It's the momenta. And these are the protons. Well, the protons fly to the direction where the bond. So nice image of the protons. And you look for the carbons. Well, from the time of flight, you can distinguish protons from carbons. Here are the carbons. That's the nitrogen. Here are the carbons. That's a ring. So there's one which doesn't fit. There is a carbon seemingly in here. Why is that in here? Well, because it's momentum, and this iodine flies this way, so it pushes its bonding partner in the ring, so it does this, and it gets bounced in there. So you see how it actually explodes. Okay, so that's kind of the biggest molecule we have done so far. So from there, we want to move to some dynamics, and I show you one movie with some dynamics, and because it's really my favorite thing, this helium dimer, I will show you some dynamics in the helium dimer. Well, if you think about dynamics, to make dynamics in quantum mechanics, you need at least 2 states to superimpose them, which are not degenerate, and in helium, this doesn't exist. There are no bound excited vibrational states. There are no bound rotational states, just one state. Quantum mechanics would tell you no dynamics, but still you can try. So the experiment we did is make, in that arrangement, make the helium dimers. Then we shoot a weak pump pulse, weak meaning 10 to the 14 watts per square centimeter. That's just such that it doesn't ionize. It only changes the polarization a little bit. By that, it changes the interaction strength of that dimer, so it changes this here a little bit. And then we came time delayed with a very strong pulse, several times 10 to the 15, and Coulomb exploded it and then changed the time delay to make a movie. If you would do the same setup with a stiff molecule, with a tightly bound molecule, you would induce rotation. Here, you have to look more detailed at the potentials. What this strong field does is it changes this native potential. If the molecule is perpendicular, it makes it unbound. It changes to this. If the molecule is parallel, it changes to this. So what you do is actually in this tremendously big wave function, you change for a very short time, like, well, for this weakly bound thing, 100 femtoseconds is short. You do for a very short time, whoop, whoop, in here. Now the question is, so you only affect this inner part. How does the whole wave function react to that? Out here, you don't change the potential because they are so far away, they don't see that. You just disturb the wave function in here. Now you can watch what happens out there. And does it react all as one and blow apart, or is there some dynamics? So what could you expect? I mean, either the whole thing breaks apart, or something starts from in here. And if something starts from in here, maybe you have a wave packet outgoing. So here's the experiment. Maxim Kurnitsky did that in the lab. So what is plotted here is the density as function of time minus the ground state to make small changes visible. So it's a signal on that thing. And here comes the pulse. And that is the density distribution, well, this difference, which you see. So this wiggle runs down the hill here. Okay, what is it? Is that a wave packet? It doesn't look like my cartoon of a wave packet. It has a lot of structure in there. What is that? So first thing you can do, make a calculation of a real wave packet in the real potential which you induce, and that's the real wave packet. Now for the real potential which we did. So that doesn't look like that. But what is plotted here is the square of the wave function of that wave packet, of that outgoing wave packet, the density. But I mean, here is more structure under here. So let's look at the real part. Now let's also look at the phase of the wave packet. Now same wave packet as before, but not the square of the wave packet, but the actual including the phase, the real part. And that's what the wave packet looks like if you could measure the phase. And if you now look at the movie down here, you recognize that that's what you see. You see a wave packet going out, including the phase of the wave function. How can that be? We measure densities. How can you see the phase in there? And simple, it's pretty simple. I mean, all of you know how to measure phase of something, of light, by doing interferometry. So what's the interferometer here? The interferometer is a very simple one. We have the ground state that's this completely delocalized thing. It's real valued, but it's spread out, and that makes a quantum background. And on that quantum background, this wave packet goes out. And you have the interference between this delocalized real valued quantum background and your outgoing wave packet, and that interference creates this image of a free-flying, there's no potential out here, of a free-flying wave packet, including its phase. Okay, so that was the movie I wanted to show you. Now we move from nuclei, we move to the electrons. Can we also image electrons? Well, I know in Ottawa, so you have imaged molecular wave functions very, very beautifully by doing higher harmonic spectroscopy. Higher harmonic spectroscopy is the inverse of photoionization. So if it works with high harmonic generation, if you capture an electron and emit a photon, if you somehow, the wave function is in there, also the inverse photoionization should somehow give it. So the dream would be to get this by shooting high energy photons, kicking out the electrons, and then hope that we can smash that to the detector and then make it in coincidence with here. But of course, that's only the hope. There are many obstacles, and it's not so easy. First, we are in the gas phase. These molecules are randomly oriented. Well, we can fix this, because for each molecule, we measure its orientation in space, so we can relate our electron to a molecule which, at the time when we kicked out the electron, had a certain orientation. So that we can fix this gas phase problem. But then there is another problem, which everybody who does high harmonic spectroscopy knows very well. That is that electrons, which you emit from a molecule, don't fly straight to your detector. But they have molecular potential. And they meander around and then get scattered and get out. So the momentum which you measure is not the bound state momentum, but something which is modified by this potential energy surface, complicated potential energy surface of your molecule. And you cannot ignore it. In high harmonic spectroscopy, everybody knows you have to go to high energies to make this thing a plane wave. So the only thing to do is high energies, then the outflying electron doesn't see this bumpy surface, and it goes straight to your detector. And we went to 400 electron volts, where the plane wave approximation isn't perfect, but it's decent. Okay, let's do it. H2, that's H. Is that an interesting wave function? Well, for the electrons. That's coordinate space, that's the cartoon, that's a real calculation. It's a dumb, super dumb wave function in coordinate space, almost round. It's almost like a hydrogen atom. We measure in momentum space, so let's take the Fourier transform from this. Well, it's still dumb. It's still almost a circle. Well, it's a little narrowed perpendicular because it's in position space. It's more extended here, so by the uncertainty relationship, the momentum is a little narrower, a little more extended here, but besides that, it's boring. No point in measuring it, but Now let's switch and look for the details out here. That's a linear density scale. And I guess you've probably never looked on a highly logarithmic scale on an electronic wave function, because even for a dumb molecule like this, you see a lot of structure in there. That's a super logarithmic scale here. And you see nodes in this wave function momentum space. If you think for a moment, it's very natural, because you have 2 points here. If you do the Fourier transform, you get a sinusoidal thing, and that's what you see here. So it's, once you've seen it, it's very obvious, but I wouldn't have guessed that it looks like that. Okay, so that's the wave function. Now, if we eject by absorption of a single photon, the electron, how does that map that wave function? The electron flies out. The photon does not, in perturbation theory, does not accelerate the electron. This electron just is taken to the continuum with the momentum it had in its initial state. The photoionization in perturbation theory basically cuts the bond between the nucleus and the electron and sets free, by supplying the energy, sets free the momentum the electron had in the initial state. And if you have a certain photon energy, you can only talk to the electrons which are out here. So you map out these electrons from the ground state. That's the idea. So if you do a line out of that wave function out here, just a wave function, not experiment yet, you get that density distribution. So these are the nodes here. Now, if we do photoemission takes these electrons and puts them to your detector. And now I show you the picture from photoemission, including a calculation which is not my simple plane wave approximation. In the plane wave approximation, you will get exactly that. That's a real high-level calculation. And you see the plane wave approximation is not perfect. You get a little more here. But the nodes are exactly where they are. So yes, you see details of the wave function, including the nodes. That wouldn't be so exciting, but in helium, there are 2 electrons. And I've shown you only one here. So the real helium wave function, of course, there's electron A and electron B, which are identical. Now, if you calculate the 2-electron wave function with a quantum chemistry code, you could do that, for example, in Hartree-Fock approximation. Hartree-Fock approximation would say, well, you take one electron, change the potential, and then you get the eigenfunctions which fit best, and both electrons are in the same function, Hartree-Fock function, which is 1 sigma g, that's the ground state, and it's just a product of these 2. Both electrons are the same, and that would be the outline which you get. Electron A looks like that, and electron B looks exactly like that. And it was kind of what I've shown you. But that is only true in Hartree-Fock approximation, where the electrons don't know of each other. For example, this wave function would tell you it's the same probability that both electrons are together here as they are both here, as one here and one here. And of course, that's a very crude approximation. So you have to go beyond Hartree-Fock and include correlations in your quantum chemistry code. If you do that, next correction would be you include an infinite sum of, with some factor here, some excited Hartree-Fock states. If you look at this contribution, well, it looks kind of the same. You have just this additional node here because it's a 2 sigma g. But there are more. It's an infinite series. That's the next more relevant one. And now it becomes interesting, because this series here from quantum chemistry tells you that the ground state of H2 is a perfectly gerade symmetric state. And that tells you you can build it up from partial contributions where either both electrons are gerade or both electrons are ungerade. In this case, if both are ungerade, the wave function now looks completely different, because an ungerade wave function has a node in here, and in position space, you all know that. In position space, the ground state is a gerade state, which looks like that. And the antibonding state, an antibonding state is an ungerade state for H2, which has a node here, and that node is what you see here centrally, where there is a maximum. You convert maxima to minima. Now, a high-level calculation tells you the real ground state of H2 has all of these components, and it has you can sum the gerade components and you can sum the ungerade components. They are weak, but they should be there. And if you come from a quantum optics background, that you could rewrite as a contribution of gerade states and plus both electrons ungerade, so the total has to be gerade. And of course, you have seen that. For photons, that would be a belt state. For example, for a triplet state, both pointing up and both pointing down. So this is an entangled state where both are ungerade or both are gerade. The only thing which you know is that the sum, the total thing is gerade, like here the total thing has spin 1. It's an exact equivalent. And that tells you molecules have entangled electrons. To some extent, this coefficient is small. So very natural, in any molecule, you have these contributions. Can we see them? So what we would have to do is get this image in coincidence with this, and then we would see that the two belong to each other, like detecting two photons with two polarizers and then do coincidences to prove entanglement. Now, we could do that on the detector. We didn't. Instead, we projected one electron to our detector to get that, and then the other electron we projected on bound states, which have the same property of being gerade and ungerade. And we did that by looking at that reaction. One electron out to our detector, the second electron to dissociating states of H2+, which dissociate in a proton and a neutron. And these states are of either gerade or ungerade parity. So we map the parity of that one. And you can do that, again, by measuring the energy of the proton, because if you measure the kinetic energy of the proton, the gerade state here has small kinetic energy, and that ungerade state, the proton rolls down that hill and gives a contribution here. So these are calculations from Fernando Martin. Okay, so we look at the electron on our detector in coincidence with these or these fragments, gerade or ungerade other electron, and see what we get. So that's the one with the gerade state, which I kind of already showed you. That's a calculation of the wave function. That's a line out in here, and that's photoionization. So you very well see that there is a central maximum. That's a gerade state. It has constructive interference. The molecule lies here. So you have a central maximum that is a gerade state where you have constructive interference in here. And now the ungerade contribution should have the node in here. So that is the wave function if you take that line out. And that are the coincident data. And you very well see there is this node. So if one electron is ungerade, the other one is also ungerade. If one is gerade, the other one is also gerade. Now, if you are in chemistry and you stop your chemistry code at the Hartree-Fock level, you would get 0 counts in here, and that wouldn't exist. Now, the relevance is from that coincidence, you see two things. First, you can visualize, by photoionization, you can visualize correlated wave functions beyond Hartree-Fock, which is very hard because there are small corrections. And the second part, which is fun, you can see on your detector that electrons in molecules are indeed an entangled many particles state, which is not surprising, but you can see it on your detector. So I guess I have 5 minutes, so I skipped these details here. And instead I will show you some brand new unpublished data, because this is Ottawa and Paul is sitting in the first row, so I have to talk about attosecond science or something faster than attoseconds. So here's a time measurement. I remind you of the time scales of interest for molecules. If we start in the femtosecond regime, there we have access, that's the time scale of nuclei vibrations, and the benchmark there is the fastest thing is vibration of hydrogen. That's in the 10 femtosecond regime. So with 10 femtosecond time resolution, you can see molecules vibrate. Now, you could stop here and say, well, nuclear motion is what interests you in chemistry, but of course the electrons drive the nuclei, so you want to see also electronic motion, and people have done that, so that is what attosecond science is. You go to attosecond time resolution, and what you can see then is electrons moving in bonds or in solids, And you can also time the process of photoionization, which I've discussed, so you can estimate how, or measure how long it takes for an electron after absorption of a photon to escape from the potential. And if you do that, the time scale there is in this range here. And a benchmark to remember is an electron in a hydrogen atom to go from one side to the other is 50 attoseconds. So that's time scale for electron motion. And with that, maybe you would think that's the end. Chemistry, you are done with attoseconds. Is there anything faster? Yeah, of course, there is something faster than electrons. There's light. Light's faster. So what happens in a molecule or in photoionization on the scale of the speed of light? On the speed of light, you go to septoseconds. And to give you again a number, the number there is it takes a photon in the highest molecular orbital of hydrogen. It takes a photon to go from one nucleus to the other. It takes 230 septoseconds. What could happen there? Well, photons, if you want to measure photons traveling, that's the time scale you have to approach. Also entanglement, well, entanglement we could discuss. It's either bound to the speed of light or instantaneous. So if you want to learn about that, you have to have septosecond time resolution. So can we do it? So here's an example what the question would be. If you have some extended molecule that is the HOMO of, I don't even know what molecule it is, but just to pose the question. How long does it take to ionize that? One question is, how long does it take the electron to get out? That's answered, that's attoseconds. But you could also ask the related question, does the photoelectron wave start instantaneously from the whole orbital? Or maybe the photoelectron wave starts first at one part of the orbital and later there, depending on from where you come with your photon. I mean, the photon hits here first, so maybe the electron wave starts first here, and then you would, to see that, you have to have septosecond resolution. Of course, we didn't do that for this molecule. We did our favorite H2. Here we have 200 septoseconds to resolve. And that's Sven Grundmann, and he would probably hate that I show it to you because next week he is rerunning it, but I believe his data are correct, so I show it. Well, you can judge yourself. So how can you measure times? Well, you measure it in quantum mechanics by measuring phase differences, if you know the wavelengths, which for electrons you do. And if you have short wavelength electrons, then you can go to very short timescales by doing interferometry between electron waves. Now, for photoionization of any homonuclear diatomic, long time ago, Cohen and Fano have pointed a very nice analogy to be very precise, actually. If you photoionize H2 or N2, it's very close to a double-slit experiment. Your photoelectron wave starts from the HOMO, but photoionization grabs the electrons when they are close to the nucleus, so you have the wave going out here or here, and that gives an interference fringe. That's in the prediction of that paper, and has been seen in many experiments. So for 800 eV photons ionizing from H2, that's Sven's result. You see this interference fringe from the fact that photoionization of a homonuclear diatomic is to a very good approximation, is a double slit. Now, that's the angular distribution. Now, the wave function behind the double slit, that's the square of the wave function. You see the central maximum and then the destructive and so on. Now, what would happen in the double slit? What does interferometry tell you if you have a little time delay between the emission from the two slits? So you add a little phase to one, and what happens to the interference? Well, you tilt it a little bit, whether it starts here or on the other side, so that's what you should see. So if there is a time delay, this thing should shift. So measuring this interference fringe here is super fast. Watch where the arm of the clock is the central point here, and if you calculate the wavelengths, that has septosecond resolution because the wavelength of the thing is so short. you have 800 eV, so that's a very short wavelength electron. So let's see if Sven sees something. You come in with a photon from here, so the two are by definition at the same time, so this thing is in the center here. That's an electron. This means the electron is emitted constructive interference from here to here. Now you come with a photon, or you select events where the molecule was oriented such that the photons came from here. In reality, we measured it in coincidence. So that's what he gets. And now you have to look for the central line, and you see it's a tiny bit of shifted. Okay, cross-check, other side. Okay, it moves a little bit to the other side. So this arm of the clock, hand of the clock, does indeed move. And if you are not convinced by this data, Sven wasn't, you can plot it. That's the angle from where the photon comes, and you see, and that's the central fringe here, and you see it indeed has a tilt. And from that tilt, you can measure the time difference for these extreme cases. And if you do that, it's not finally analyzed. You get exactly to the ballpark. So that's a stopwatch on the septosecond regime. And the bottom line, what you learn from it is, yes, photoionization of an atom, of a molecular orbital is not instantaneous. The orbital does not react as one. It reacts first on the side from which the photon approaches. Might not be too surprising, but it's nice to see it. Or you could call that retardation in photo emission. The photon wave needs some time to travel across the molecule, and that makes that you measure here, and the time is septoseconds. Okay, and that's Sven Grundmann, who will redo that next week in Hamburg. And with that, I'm at the end. I would like to thank all the collaborators. So that's the team in Frankfurt. And Sebastian Eckert is here. So if you want more details, you can talk to Sebastian. The helium-2 work was mainly done by Maxim Kunitsky, the chiral molecules by Martin Pitzer, and the H2 wave function by Markus Weitz and Sven Grundmann you have just seen. With that, I thank you for your attention.
Right, very nice. I have a question about the last part of your talk and actually about the dipole approximation. So if I just think naively, when I make the dipole approximation, what I have to write down the light-matter interaction, and then I make an assumption that the electric field is spatially uniform on the length scale of the molecule, and this allows me to make this dipole approximation. Seems to me in some sense, this is what you're saying, that this is really a failure of the dipole approximation. And so are you, in a different way, saying that there are other examples of non-dipolar interactions when the photon energy becomes very high? Can these, in general, non-dipole light-matter interactions be used to get this idea of a time scale that you're suggesting?
Yeah, that's exactly the suggestion. If you look at the dipole approximation, I mean, the photon people have done that for a long, long time. Like they have looked for phase shifts in molecular photoionization for a long, long time. And all of these insights, which we have gained from discussing on the phase level and on the dipole level, you can interpret in the time domain. That's true for phases, which you can interpret as times, and it's the same here. So what I'm saying is in the non-time independent approximation, you call a breakdown of the dipole approximation. In a time perspective is a time from different positions. That's what I'm saying.
Thank you.
So I want to thank you for your talk. I understood a remarkable amount for someone with my background sitting in your audience. So I think you did a very good job of explaining lots very clearly. I have a question specifically about, I guess what we'll call your molecular movies section. If you could please go to that animation, because I'd like to point something out.
I'm not so sure. This is not my computer, but I will manage it.
So I have a nanophotonics background. When I picture a potential, I think of a high-index core of a fiber. And so you're describing kind of a potential that reaches way out beyond where the interaction is. So in my mind, yes, this. So in my mind, I'm picturing just like an evanescently guided fiber. And then what you did was you modulated just the index of the inside of the fiber, and then it let out light. That totally makes sense to me. Uh-huh. What I'm curious about is when you play this animation, so if you could please do that now, in your, I guess, theory curve on the top, it looks to me like you have some ringing on the inside of what I'll call the fiber. It looks like you have some ringing. It goes up and down. See that right there?
This thing here.
Yeah, that little guy right there.
That's an artifact of the simulation.
Oh.
That's an artifact of the simulation. Our grid wasn't fine enough.
That is very disappointing.
I'm sorry, and I'm not so sure how far you can go with this analogy.
Yeah?
I haven't thought about that in detail. Maybe somebody who has more background on both levels than I do could help me with that analogy. I understand it. It sounds logical, but here I have to disappoint you. That's not real.
Okay, thank you.
Hi. So I find your, especially the helium molecule, very interesting. But one thing I don't really understand is what would happen if you hadn't a bound state. Because if you have a continuum and you modulate it with a potential, there would be still some like stacking of density of states, and you would have something like resonance, like a Fano resonance, for example. So you would be still in a continuum, and you would have something which has like a two-particle correlation function, which also should decay exponentially. So I'm wondering if the distribution that you showed us is actually, uniquely determining a bound state from a possible resonance, which is not really bound.
This thing is bound. Well, how do you know that it's bound? That it lives for a very, very long time. So you can, I mean, a resonance has a decay time, and this thing, the first thing from theory, you know that it's bound. In the experiment, we only know that it flies in our supersonic jet about this, and that has a speed of 2,000 meters per second. So you can estimate for that time it lives. So if it would be a resonance, it would have to live on a macroscopic timescale of milliseconds, because the way we make it in a collision from a supersonic expansion, then it travels through our chamber with kind of slow motion, so to say, and then we hit it. And actually the machine for the helium dimer, we have done it with this traveling, and now we have a machine with about this size. And the Tönnies group, who has first discovered the helium dimer, had a machine which was 3 meters long, and it still survives, and there was no decay seen. So I don't know whether there are more arguments needed. So I'm very sure, in agreement with theory, that it is a bound state. When you excite it, that is this decaying state. That is, well, we know only from theory that there are no resonances. And of course, we cannot tell from the experiment. You see the superposition of the outgoing wave packet with the ground state, which makes that. And that's all we have. You can get the phase velocity from it, but that I cannot exclude.
Yeah, because I mean, I would expect that the decay time would also scale with the binding energy, which is extremely small. Yeah. So yeah. Okay.
Well, the only answer I have, there are no predictions of Fano resonances in here.
Thanks, Paul. And thank you for this wonderful talk. I have a question on these very interesting results that you showed at the very end. And please correct me if I misunderstood, but I think that you do not control the orientation of your hydrogen molecules. And furthermore, you don't even know what is the orientation.
Yeah, we do know.
You do know.
We do know. We measure, sorry.
So that's perhaps my question then. Okay. How do you interpret the measurements that you have in terms of molecular orientation?
We do know. We do the coincidence with the breakup and the electrons. And so from the breakup, that's very violent, and it breaks up along the bond, as I've shown with the other examples. We measure on one detector, we measure the direction of breakup, so we know. Of course, that is random. Each shot gives a different orientation, but we have in correlation the electron. So we can rotate it, the electron, in software, to the frame of where the bond was, and that is what I've shown you. So that was in the molecular frame. That was not the coordinate frame in the laboratory, these interference fringes. It was with respect to the molecular bond inferred from this very, very good approximation.
From the breakup maps.
Yeah.
Okay.
It was really from the coincidence.
Thank you.
This question, I hope I formulated well, but it's also related to the last experimental results that you presented. How would you, like, the electron is either absorbed the photon and kind of escaped and the two atoms, or it didn't.
Yeah.
Like you have these two situations, but the electron can be in any position when that happens. Like it's not like one part of the cloud will absorb and the other will not. It's so how does that fit in? Like the cloud is a kind of like a possible location of the electron, but the electron can be anywhere. So when that absorption happens, it could be anywhere. So how does that?
I mean, my answer would be that is how a quantum measurement actually works. I mean, quantum mechanics gives you the wave function, and from that you get the distribution. But each individual measurement gives you 1 point, because you don't measure the distribution. In a single observation of any quantum measurement, you measure 1 point, and then you do that many, many times, and with that you get the probability distribution, which is the square of the wave function. So, of course, for the individual electron, you don't know. You measure the square of the wave function by measuring the probability distribution of your counts. And I would believe any quantum measurement works like that. You sample a wave function by individual experiments which give exact values. I mean, it's the uncertainty and the wave function doesn't mean that the position is uncertain on the individual. Every individual measurement gives you an exact value, which is not limited by the uncertainty relation by nothing. And only if you sample many times, the results will scatter according to the calculation. So maybe we can discuss later.
Thank you.
Maybe I missed it. Thank you very much. Thank you.